in the context of working with vectors, one of the important things that you'll do with vectors is what's called scalar multiplication. And this word scalar, when used in the context of vectors, really just means a real number, or sometimes it can mean a complex number. But in our case, since we're mostly working in Rn, we're going to be mostly working with real numbers. So in our applications, we're going to, anytime you see the word scalar, just remember that that's just a real number. And so we have some particular letters that we sometimes use to denote those. Often we use C or K, or sometimes A or B, or things like that, often used to represent a scalar. All right, so what we want to talk about today, though, is what's called scalar multiplication. So this is the idea of taking a scalar, C, times a vector, V. So I'm just going to write that kind of using that same notation that we've used before. So I'm going to use C for my scalar here. And I'm going to write the vector here in terms of its components. All right, so here we have scalar, and then right next to, so in general in math, when you see something like that, where you have something right next to something else, that would be multiplication. So scalar times this vector. So we're going to define what that means algebraically, and then we're also going to look at the geometry of what that means. So the way that's defined algebraically is it looks like you're just doing a distributive property here, but you're just multiplying each component by that scalar. So when you have scalar times a vector, just each component of that vector gets multiplied by that scalar. And if we look at this geometrically, you can see a little bit why this might be called scalar multiplication. So if I take a vector, say, we'll just do one in 2 dimensions here, so it's easy to draw and look at. So let's say that I take a vector that is, say, 1, 2, and then I multiply that vector by, say, the scalar 3. And I'm going to look at those two vectors here. So if I take 3v, so that's going to be 3 times the vector 1, 2. And so using this definition that we have here, so it'll be 3 times 1 and then 3 times 2. So 3, 6. And if we look at those two vectors and see what happens geometrically, when we do this, you can see that if I draw my vector in standard position, so tail at the origin, my original vector v, 1, 2, draw that here. So there's my vector v. And I'll use a different color here to do my vector 3v. So my vector 3v, if I draw that also in standard position with tail at the origin, so I need to scale my axes a little bit more here. And put my terminal point over here from origin to there. You can see, and certainly if I would have drawn this especially perfectly, you would see that really these two vectors are in the same direction, but what's happened is I now have a vector that is 3 times as long. We could calculate the lengths of those two vectors, and you would see that this new vector is 3 times as long. I can fit 3 of those vectors that goes over 1 up 2, over 1 up 2 into that space. So this indicates a little bit why we use this word scalar. One of the applications of scalar multiplication, is this idea of rescaling a vector to a different length. So I'm going to list over here some important applications of scalar multiplication. So one of them is to rescale to a new length. And so if we want to kind of think about that here, you can easily calculate the magnitude of this first vector would be square root of 5, using formula for magnitude of vector. And then the magnitude of this vector would be square root of 45, which is 3 times square root of 5. So you can see that multiplying by that scalar 3 rescaled the vector by 3 times as much, to a length of c times as much in general, by factor of c. All right, another thing that we might think about is what if the scalar that I multiplied this vector by was a negative scalar? So let's just go back to this example here and think about what if I had done say negative 1/2 v. So negative 1/2 times my original vector v, 1, 2. So I would get the vector negative 1/2, negative 1. And so if I sketch that vector with its tail at the origin, I would go left 1/2 and down 1. I didn't scale my axes here, but we can fix that. Left 1/2 and down 1, we'd get a vector over here. And that new vector then, negative 1/2 v, is half as long. Can calculate the magnitude of that, half as long as the original vector that I started with, and in the opposite direction. So technically, to fix this up here, I would probably want to add something to that. I'm rescaling to a new length by a factor of technically the absolute value of c, right? So half as long. The other application that we might use scalar multiplication for is what I did right here. When I use a negative as my scalar, that will turn the direction of the vector around to be the exact opposite direction. So that's something we will do sometimes. Sometimes we'll do some calculations and we will get a vector, but it's pointing the exact wrong way for the vector we need for whatever application we're doing. So we'll need to turn that around by multiplying by a negative. And if we don't want to change the length, then just negative 1. So another application would be to switch the direction to the exact opposite direction. So that would be by using a scalar c equals negative 1. And then the other thing was something I alluded to in the last video, and so it's kind of a combination of this. But if we want to think about rescaling so that we end up with a vector in the same direction as our original vector, but whose length is 1, not 1 times as long as this, but whose total length is 1. So you're going to want to change that vector. So you're going to want to change that vector by a factor of whatever its original length is, so that you get a vector of length 1. So this is another important application. I'll put a little asterisk by this one so you'll remember that that one's really important. But to rescale a vector, to get a unit vector, in the same direction as your original vector. And so to do that, you're going to multiply by 1 over the magnitude of the original vector, and you're going to multiply that times the vector that you've started with. So this will give you a unit vector in the same direction. So if I wanted to do that with this example that I have over here, this vector that I started with, that is 1, 2, and we said its length is square root of 5. I could get a new vector that's a unit vector. I'll maybe label that u for unit vector by multiplying this vector here, 1, 2, by 1 over square root of 5. So if I go ahead and distribute that 1 over square root of 5 in, I get 1 over square root of 5, 2 over square root of 5. And you can verify by doing calculation that that vector has length 1, but that vector would be along my vector v, but length 1. So I maybe need some decimal approximations to help me a little bit here with where to plot that, but probably about right there would be that vector of length 1. So anyway, these are important applications for scalar multiplication. So you want to make sure that you know not only how to do the scalar multiplication, that's pretty straightforward, but why you would do the scalar multiplication, so that when you're doing something else, you recognize, oh, I need to use scalar multiplication to accomplish this goal that I'm working on.